Welcome to Section 6, Sequence Modeling with Recurrent Neural Networks. In this section, we're going to talk about recurrent neural networks, how they work, when to use them. We're going to talk about LSTMs as well, which is an improvement upon the original RNN, which solves a lot of the issues with long-term dependencies that often come up with vanilla RNNs. We're going to use what we learned to build a Twitter sentiment classification, similar to what we did back when we used bag of words to classify, but now we're going to use an RNN to do this, and we're going to see that we have an improvement in the performance because we're able to handle these long-term dependencies a whole lot better. Lastly, we're going to build a cryptocurrency price prediction bot using RNNs to model time series information. So, welcome to video 1 of section 6, Understanding Recurrent Neural Networks. In this video, we're going to talk about what RNNs are, how they work, and why they're best suited for these sequence tasks better than other models that we might have encountered before. So traditional neural networks look like this, as we've covered in the last section, where we have an input layer, a hidden layer, and an output layer. RNNs are very similar, except each of these nodes is something different. So we're going to take a look at just one of these nodes to see how an RNN is different from a typical neural network. So in the typical sense, we have a node, this H, that takes an input and produces an output. This is very standard. The difference with an RNN is that this node also takes its input from the previous time step. The way this works is the model receives an input, it produces an output, and then it feeds that output back into itself so that it can produce also at the next time step. So it's a little complicated to look at it just in this recurrent form with this circle. So an often popular way to visualize this is by unrolling the RNN through time, is what it's called. So unrolling or unfolding is what we do here, in that we have our input at time t minus 1. So we have x of t minus 1 goes in to our node, h of t minus 1, which is our activation, and it produces some output, o t minus 1. At the next time step, time t, we input the input of x of t, and we get an activation of h of t, and we produce an output of o of t. And what we do is we feed in the output from the previous time step into this, and we repeat this. And the power of what this allows you to do is that you can build up representations successively through time. So in the case of something like natural language, each of these time steps, each of these inputs at these different time steps would be a word in the sequence that it appears. So as we read a sentence as people, we build up an understanding of what the sentence means by taking into account what we've read previously. This is the power of the recurrent unit, is that each time it processes a new word, it receives a context, this v vector, from the previous time step. And by keeping track of this context, when it sees a new word, it understands in the context that it appears in how to best handle it, how to best process it, whether to ignore it, what the word means in the overall larger global context. So we've talked about this previously in the natural language section, but in something like sequence modeling, the order of the words matters a whole lot, and the more context that you can capture, the more powerful your models are going to be. So the more prior words we can incorporate in our prediction of the next word, the more accurate we're going to be at that prediction. When it came to something like bag of words models, as we've used previously, there was a limitation in how many contexts we could have, how many words back we could actually look, because the state space really grows exponentially. So in comparing n-grams to RNNs, the most important thing to note is that n-grams are limited in their context. They can't look back too far because the space gets too sparse. RNNs, on the other hand, have this property of near limitless context. They can handle long sequences, and by using this context vector to pass in at each new time step, it can learn to use what is proper. The second thing that's core to the same thing is that n-grams struggle from sparsity. As n grows, we don't see a lot of these longer sequences very often, so we get a very noisy representation of it. However, with RNNs, we have a shared representation at each step, so this is a powerful way to overcome the sparsity problem by learning these dense vector representations for each context or each state space that we're in. And because of this, n-grams really struggle with long-term dependencies, whereas RNNs can handle these long-term dependencies much better.